Now let's consider the design, construction and working of a first order low pass Butterworth filter. A first order low pass Butterworth filter is an active op-amp based filter that has a characteristic high corner frequency up to which it will allow any input frequency or operating frequency to pass through it, and if the frequency of the input signal is exceeding this high corner frequency or characteristic corner frequency, the signal will be attenuated at a roll-off of 20 dB per decade. We will now see the construction, design, working of a first order low pass Butterworth filter. The passive filtering component of the circuit is this pole consisting of a series combination of a resistance R1 and a capacitor C1. The active component is of course the op-amp non-inverting amplifier, so that the signal that is to be filtered is injected to the non-inverting terminal of the op-amp, and resistances Ri and Rf are given to the inverting terminal so as to fix the gain of the amplifier or the active component. For first order Butterworth filter response, that is flat filter response with the stop band having a gain variation of 20 dB per decade, you can have any value for the gain. The gain of this amplifier, as you know, is 1 plus Rf divided by R1. 1 plus Rf divided by R1. You can have typically any value of midband gain as fixed using this resistance ratio Rf and Ri. Generally, there is a rule of taking the midband gain of a Butterworth filter that is generally given in terms of the value of the Butterworth polynomial of relevant order, so that midband gain of a first order Butterworth filter will be equal to 1 by polynomial value of Butterworth polynomial having order 1. Its general expression for this is midband gain A is equal to 1 by Pn of S, where Pn is the Butterworth polynomial of nth order. The Butterworth polynomial of first order is S1. The coefficient of S is 1 here, where S is j omega. Since the coefficient is 1 here, the gain can be any value. So you can have a first order Butterworth filter having any midband gain as fixed using this ratio Rf and R1. The magnitude of the gain of a Butterworth filter also will be following a characteristic equation given by the expression A magnitude of the filter AF is equal to magnitude of the amplifier, that is the active component in the Butterworth filter, that is the op-amp configuration, divided by square root of 1 plus omega, that is the operating frequency, that is the frequency of the input signal, divided by omega c, which is the angular characteristic corner frequency raised to 2n, where n is the order of the filter. So omega by omega c is of course f by fc. So the gain AF is equal to A by root 1 plus f by fc all raised to 2n. If it's a first order filter response or a first order filter, n can be taken to be say 1. So AF equal to A by root 1 plus f by fc whole square. For a second order filter, you have to take n equal to 2. This is the general empirical formula. We will be proving some of these expressions depending upon the order of the polynomial. Say for example, we will prove it for first order. We will take the empirical formula for the second order. And as per the demand of the syllabus, we will have to make qualitative analysis of first order and second order filters only. Now let's consider the working of this filter. As I have already told you, there are two different components in this active filter. The passive filtering unit, that is this RC network, being designated as a pole having a characteristic corner frequency 1 by 2 pi R1C1, and the part that will be offering the active modification for the filtered signal being filtered by this RC network, that is this operational amplifier in non-inverting amplifier configuration. So this will offer the necessary gain, and the presence of this op-amp is sufficient to make necessary modification for the frequency of the filter response. That is, it employ frequency fidelity and frequency scaling for the filtering unit. So once you write it or present it for the examination, you will have to take the working in two different points for all of the RC network, which will be functioning as a passive low pass filter. This is basically a pole response. We have already analyzed. The pole will generally have a characteristic corner frequency such that if the frequency of the input signal is less than the characteristic corner frequency, it will be allowed to pass through the filter. And if the frequency of this input signal is exceeding the characteristic corner frequency, then it will be attenuated. In the stop band, this single RC unit is capable of providing a roll-off of 20 dB per decade, which is identical with the roll-off of 6 dB per octave. Roll of the op-amp, that is the active component in the circuit. The op-amp is designated in non-inverting amplifier configuration, so that this will offer a gain of 1 plus Rf by R1 to its input, that is being labeled as the voltage across this capacitor, say Vs, and Vi is the input to the filter. This much portion corresponds to the amplifier and this much portion corresponds to the filter. So the amplifier input is Vs, that is the drop across C1, and the filter input is Vi. If you are looking into the amplifier gain, then output will be equal to 1 plus Rf by Ri into Vs, and for the filter, the output-input relationship is essentially Vo divided by Vi. Now we will consider this input-output relationship. Vo, as I have already told you, is equal to 1 plus Rf by R1 into Vs, where Vs is the amplifier input. But Vs is equal to the drop or the part of Vi dropping or appearing across C1, that is Vi by net EMF Vi by total resistance R1 plus 1 by j omega C1 into 1 by j omega C1. You can cross multiply this. 1 plus j omega R1 C1 divided by j omega C1 vanishes, that we do here. So Vo is equal to 1 plus Rf by R1 into Vs. We substitute this value of Vs here, that is 1 by j omega C1 into Vi divided by 1 plus j omega C1 R1 divided by j omega C1. Take Vi to the left side, we get an expression for the gain of the filter, Vo by Vi. Gain of the filter, Vo by Vi equal to 1 plus Rf by R1, j omega C1 vanishes, divided by 1 plus j omega C1 R1. Of course, we substitute this as the characteristic corner frequency of the low pass filter, Fc. Generally, Fc is also labeled as a characteristic high corner frequency of the filter, because this is the maximum frequency that will be allowed to pass through in the midband region. Fc is equal to 1 by 2 pi R1 C1, and we substitute 1 plus Rf by R1 as A equal to 1 plus Rf divided by R1. Now fixing a particular value for Fc and taking different values of operating frequencies or the input frequency, we will tabulate the variation of the gain. For that, first of all, we will have to evaluate the gain magnitude. Gain magnitude you can evaluate from this one. This is a complex gain. This we substitute, say AF is equal to A where A is 1 plus Rf by R1 divided by 1 plus J into F divided by Fc. Now you decompose this complex gain into its real and imaginary part. For that, we will have to multiply this gain by means of the conjugate of the denominator. Then you will get the real part as A by 1 plus F by Fc square, and imaginary part as A into F by Fc by 1 plus F by Fc whole square. We have already made this analysis in the circuit analysis of the effect of a pole in a circuit in the last chapter. You can refer that too. And to evaluate the magnitude of this gain, you have to take the resultant of the real and imaginary part of this complex gain. That will turn to this empirical relation AF equal to A by root 1 plus F by Fc whole square. So AF equal to A by 1 plus J into F by Fc. So AF magnitude, you can prove it as A by root 1 plus F by Fc whole square. And phase difference phi, of course, that is minus tan inverse of F by Fc. This is a lag network. Now we have to make the analysis. For that, we will take, say, Fc equal to 1 kilohertz and tabulate the values of F, the operating frequency, F by Fc whole square, since you have F by Fc whole square in this expression, and decibel gain 20 log A minus 10 logarithm of 1 plus F by Fc whole square. And if you are interested, you can put the next column as the phase angle phi as well. And what we see is that as the frequency is very small, the gain is a constant, that is A. As the frequency increases, the second point, as the frequency increases, the gain continue to be constant. As the frequency become equal to Fc, the gain is found to be 3 dB lesser than the maximum gain. So this can be taken as the passband extreme point. If the frequency increases beyond this corner frequency Fc or Fh, the gain is found to be falling at a roll-off of 20 dB per decade. Next point, this roll-off of 20 dB per decade is identical with a roll-off of 6 dB per octave. That also you can prove from the tabular column. Next point about phase difference. For low frequencies, the phase difference is 0 or negligible. As frequency increases, the phase difference also increases. At Fc, the phase difference is 45 degree. If the frequency increases beyond Fc, the phase difference between output and input will be rapidly tending to 90 degree. So the analysis is based on this table, and following this tabular column, you can draw a curve between frequency taken along the x-axis or log frequency taken along the x-axis and decibel gain taken along the y-axis, and you will have to label the characteristic corner frequency of the low pass filter as FH, high corner frequency എന്നാണ് ഇതിനെ പറയുക. അങ്ങനെ പറയാൻ കാരണം ഈ വാല്യൂ ഓഫ് ഫ്രീക്വൻസി വരെയാണ് പാസ് ചെയ്യുന്നത്. അപ്പോൾ പാസ് ചെയ്യുന്നതിലെ മാക്സിമം ഫ്രീക്വൻസി FH എന്നുള്ള ഈ ഫ്രീക്വൻസിയാണ്. അതിന്റെ മുകളിലുള്ള ഫ്രീക്വൻസിനെ അത് അറ്റന്യൂവേറ്റ് ചെയ്യും. Here you will have to write down the slope of this stop band line, that is 20 dB per decade, which is identical with the usage that 6 dB per octave. Each time the frequency doubles, the gain will be reduced by 6 decibel. For each time the frequency of the input signal becomes 10 times, the gain will be reduced by 20 dB. And on the basis of this graph, you can write a note on why it is called a first order filter. Since it has only one passive filtering unit, that's an RC circuit, the stop band will have a roll-off of 20 dB per decade or 6 dB per octave. If the stop band has a gain variation of 20 dB per decade or 6 dB per octave, then such a filter is referred to as a first order filter. Of course, this is not an ideal response. For ideal response, you will have to